This pushes us to develop more advanced ways for exploring research in classification driven by a shared desire to understand space. Most importantly, that highlights an ever-evolving nature of science as new discoveries constantly one related concept deals with how matter is across the this discussion scientists track of all different times. Some reasons like galaxies, while others are largely scientists from various one such band light source distance phenomenon known as this allows scientists to therefore another concept is cosmic microwave travel by studying researchers gain insight however, this data doesn't align with the uneven gravitational pattern this dismantled possibly ties according to Rice and scientists whether the Hubble Space Telescope might have described there's a fundamental flaw in our understanding of galaxies hiding between these observations. Rice says thanks to JWS powerful researchers can now study cosmic yet despite this progress dark matter and dark remain shrouded in mystery while black holes are our attention is now being drawn to dark matter as scientists continue analyzing the foundations of modern cosmology are undergoing serious telescopes challenge existing some early universes massive galaxies this suggests one of two possibilities either galaxies that fall or our understanding one emerging idea involves adjusting standard framework in cosmology. It includes cold dark energy, cosmological lambda representing dark energy. Some physicists now speculate that dark energy barrier of time interact with dark matter in ways we don't understand. This evolving form of dark energy, also called Tesla, could explain why cosmic expansions differ across time periods. Other researchers are investigating alternative theories of gravity, such as modified Newtonian dynamics or scalar tensor fields, tweak Einstein's general relativity on cosmic scales. These models aim to address the gaps and tensions in current observations, offering new ways to explain the universe's most puzzling phenomena. Public interest under Saturn's breathtaking solar solar telescope. NASA's attention turned to thousands of distinct Hubble Space Telescope harmony and the Mars showing strange still without Voyager pressed chaos could reign. Traveling nearly a million miles a day, orbital Saturn's widespread unknown intrigue. Neil deGrasse Tyson and remains compelling insight. Only moon in the solar system with a thick known atmosphere. For famously championing the reclassification of Pluto as a dwarf planet. Tyson doesn't see this as a demotion, but as an acknowledgement of our evolving understanding of celestial mechanics. He emphasizes that orbits like Pluto's, steep, elliptical, and chaotic, are reminders of how much we still have to learn about the universe. Tyson often highlights how public interest in topics like Pluto's orbit can serve as a powerful gateway to scientific curiosity. By engaging with the unusual and sometimes illogical nature of space, people are invited to appreciate the beauty and complexity of our cosmos. Pluto, in all its orbital oddity, exemplifies that. Despite the alarms raised by some researchers, the general consensus remains. While Pluto's orbit is indeed chaotic and unique, it is highly unlikely to collide with Neptune in the foreseeable future. Still, the very possibility, however slim, serves as a potent reminder of how fragile cosmic order can be. Continuous observation, advanced simulations, and refined models are essential to maintaining our understanding of the solar system's delicate balance. Pluto's curious path may not pose an immediate threat, but it continues to challenge our assumptions and deepen our appreciation of the vast and dynamic system we call home. Potential risks of Pluto's unusual orbit, a cosmic concern. After years of studying Pluto, scientists are beginning to raise serious concerns about the potential dangers posed by its erratic orbit. One of the key issues being highlighted is the three-body problem, a complex gravitational interaction between three celestial bodies, which could, in theory, lead to a catastrophic collision between Pluto and Neptune. Astrophysicist deGrasse Tyson has warned that such a collision might be long overdue and could disrupt the delicate gravitational balance of our solar system, with possible consequences extending even to Earth. A Pluto-Neptune collision would be an extraordinary and catastrophic event. Given Pluto's relatively small size and fragile, icy composition, the impact would likely obliterate it, scattering debris throughout the solar system. These fragments could pose threats to other planets and their moons. As for Neptune, the collision could significantly alter its atmosphere and potentially even its orbit, depending on the nature and scale of the impact. Renowned theoretical physicist Michio Kaku offers a thought-provoking perspective on this scenario. Known for his work in string theory and science communication, Kaku views Pluto's orbit not just as a risk, but as a critical piece in understanding the future of space exploration. He emphasizes the importance of studying complex gravitational interactions and orbital dynamics to better navigate the solar system and to plan missions to its farthest reaches. According to Kaku, examining Pluto's orbit provides a blueprint for exploring other celestial bodies, helping scientists anticipate risks and understand how to interact with distant worlds. He frequently discusses the deep relationship between celestial mechanics and the fundamental principles of theoretical physics. The gravitational interplay between Pluto and Neptune, he notes, is not an isolated phenomenon but part of the universal laws governing motion and energy. Kaku also relates this potential planetary collision to his work in string theory, a framework that aims to unify the forces of nature by modeling fundamental particles as tiny vibrating strings. An event as energetic as a Pluto-Neptune collision could generate extreme conditions of gravity and energy, potentially offering valuable data about how fundamental particles and forces behave under such extremes. Notably, gravitational waves produced by the impact could serve as a unique opportunity to test some of string theory's predictions related to gravity and the fabric of space-time. Although Earth will remain physically unaffected due to its distance from the outer solar system, the scientific significance of such an event will be profound. It could advance our understanding of the universe's most fundamental forces and contribute to theories that seek to explain everything from the Big Bang to black holes. Pluto's peculiar orbit, influenced heavily by Neptune's gravitational pull, exemplifies the dual nature of celestial mechanics, both orderly and chaotic. It underscores how seemingly stable systems can harbor unpredictable outcomes, reminding us that space remains a dynamic and often mysterious frontier. While planetary collisions are exceedingly rare, they are not impossible. The three-body problem, first identified centuries ago, remains a powerful reminder of how gravitational influences can create unpredictable and sometimes dangerous outcomes. This principle isn't just a theoretical curiosity. It has real implications for space systems like TRAPPIST-1, which contains 7 Earth-sized planets locked in a delicate orbital dance. In the end, Pluto's orbit serves not only as a subject of fascination, but also as a cosmic warning, one that highlights the fragile equilibrium of our solar system and the immense value of understanding the physics that governs it. Gravitational forces can produce rhythmic patterns known as orbital resonances, which, over time, may destabilize planetary orbits and increase the risk of collisions. In densely packed systems like TRAPPIST-1, While the potential for interaction is high, no collisions are currently observed. Scientists actively monitor these systems to better understand how closely orbiting planets influence each other's trajectories. Adding to the cosmic complexity are rogue planets, planets that drift through space without orbiting a star. These wandering bodies are typically ejected from their original star systems due to gravitational disturbances or chaotic events, such as a nearby star passing too closely or internal system instabilities. Once set adrift, rogue planets can travel immense distances, possibly passing near or into other star systems. If a rogue planet were to enter another planetary system, there's a slight possibility it could collide with a resident planet. However, such an event is extremely rare. The sheer scale of space, combined with the sparse distribution of planets, makes direct impacts highly unlikely. Moreover, rogue planets themselves are quite rare when compared to the abundance of stars and planets in stable orbits, further reducing the chance of such encounters.